Good riddance. It's been forever since last time I uploaded something electronics related, and I hardly remember what it was about. Anyway, here's a little overview on what I've been doing this month. The big idea is still a generic way to establish communication between some UI, Windows, PC-based front-end and external devices. I experiment with the ATTiny85 microcontroller and a bucket of stepper motors, because that's what I have laying around. In a previous video I demonstrated how to control a motor directly using USB-based GPIO pins. Certainly an interesting practice project, but of course way too slow for any practical application. So the plan for the future is this. All tasks that operate in the kilo or even megahertz range must be outsourced to external microcontrollers. However, I still want to keep my Windows PC or notebook as the central point of control. To achieve this, I'm going to implement a simple I2C based communication protocol. The communication doesn't have to be fast because it simply exchanges a few bytes of information whenever I click something on the UI. In the meantime, the controller can run at its regular frequency, doing its thing, while waiting for new instructions. The finished setup is going to look something like this. On my computer, I'm going to have a simple program hosting the user interface and the front-end communication side. The IO Warrior 40 is going to be the I2C master. Connected by two wires, a breadboard-mounted ATTiny85 will act as the I2C Slave. From there, three wires connect to the stepper motor controller, and finally using the 4 coil wires to the motor. Stick around if you want to see how I did it. Defining the layout of the user interface is usually a good starting point because it forces you to think about what sort of interaction you're going to have, need or want. From there, the implementation of the backend can be derived quite easily. As mentioned earlier, my test device will be a stepper motor, so this UI will have to be all about controlling one. The first thing that jumps to mind is a couple of buttons to control the direction of rotation. I'm going to have 3 buttons for that. One for each direction and one to stop. Of course I want to be able to control the speed as well, so I'll throw in a slider. Because I don't know yet what stepper motor I'll use later, I want to keep the speed range dynamic, so I'm going to sandwich the slider between these two text inputs, where I can define the minimum and maximum speed. The slider will simply interpolate between the two, and for better usability I'm going to output the current slider value to this text element. This more or less covers basic functionality. To make things a little bit more interesting though, it might be useful to have a feature that enables manual stepping. To do this, I'm going to add 2 more buttons, one for each direction, which will start the manual stepping mode using the currently specified speed. To determine how many steps the controller should go, I'm going to add an input field and a text field to show me how many steps are left. When this number reaches 0, the motor will stop. In order to keep track of the absolute position, assuming no steps were missed, I'll have another field for that, including a button for reset. Finally, a few stats to see how the main program and the controller are doing. I might add a few more properties later, but this setup should be enough to get going. Now that we know what the front end looks like, it's time to define the communication model at the front end side. As mentioned earlier, the connection between the IO Warrior 40 and the 85 will be implemented using I2C. Now at this point I could have designed some fancy messaging protocol, but lazy as I am, I decided to make my life really easy. Here's how. I found a library that implements the slave side of the ATTiny85 as if it were an I2C EEPROM. I'll show you the details of that later. So when the controller pretends to be an EEPROM, I can simply define certain bytes in that fake EEPROM memory as a message type or payload or request or whatever I need. Communicating with an EEPROM over I2C is something I've implemented already, so I'm going to copy and paste some of the old code and be done with it. The EEPROM write sequences have the following structure. The first byte is going to be the 7-bit address of the device, followed by the write bit. This is standard I2C. The following byte is the memory location or word address, so the fake EEPROM will know where to store the data. The rest of the sequence is the application-specific stuff. The first data byte will be the mode that I want the controller to switch to, meaning left, right, stop, etc. However, I use the term loosely, so the mode can be anything really. I just put everything I need in one structure. So I guess you could call it message type. Depending on the mode, the sequence is continued by some payload bytes. Take a look at the following table. The message types left, stop and right switch the controller into the corresponding modes. Speed doesn't actually modify the current mode, it simply transfers a 2-byte unsigned integer as the new speed. The unit is interpreted as rounds per second. 0 doesn't modify the mode either, but clears the internal offset variable. This is the one that's displayed on the UI. The left and right step commands do switch the mode, but only for the specified step count. When the variable reaches 0, the controller switches back to mode stop. This one is also displayed on the UI. Now you might be wondering, why are you writing to memory location 1 and not to 0? And the reason is that location 0 is reserved for the ready byte. Here's an example. Let's say I want to set the controller to left step mode. The transfer starts, the controller detects the mode, but how does it know that the payload bytes are valid? That's what the ready byte is for. The controller checks memory location 0 periodically, and only when it's non-zero, it will evaluate the rest. Once the message has been processed successfully, the byte is set back to 0. The ready byte message would look something like this. That means that when I send a message, I actually need to send two messages, the actual message first, and then the ready byte message. Now let's take a look at the incoming messages on the front-end side. Remember when I said the ATTiny85 behaves like a real EEPROM? Well, that isn't 100% true. The difference is that the framework that I'm going to use actually has two separate buffers, one for the write messages and one for the read messages. If I wanted to, I could synchronize them by simply copying data from one to the other in every loop. The example that comes with the library actually demonstrates this. To the master, the buffers would then appear as one. But I'm not going to do that because two separate buffers are actually going to work quite nicely. The pieces of data that I expect to receive from the slave are pretty small, so I want to use a single read message that's going to read the whole block as one, maybe once or twice a second or so. The incoming bytes are assumed to be in the following format. Mode has 1 byte and serves as a feedback, so I know that the controller is in the correct mode that I previously set with one of the write messages. Offset and remaining, with sizes 4 and 2 bytes, represent the current manual stepping status and will be forwarded to the UI as explained earlier. And that's pretty much all there is on the front-end side. I can now fire it up and wait for the device to connect. The first and most important thing in preparation of the microcontroller is to get the I2C Slave framework. I'm going to use the one I found on a website called J-Tronics. If you do a little googling, you might also find similar libraries called TinyWire S and M for slave and master mode, which, if I'm not mistaken, use the J-Tronics code internally, but anyway. The framework consists of two files, header and code, which you add to your project like so, and voila, you're done. What it does, in a nutshell, is using a preprocessor switch, it hooks onto certain pins and registers that are part of the so-called USI. USI is a generic hardware interface that can mimic several serial communication protocols. In this case, the framework will use USI to act like an I2C slave, using pins 5 and 7 as clock and data lines. The required buffer size can also be modified. I don't think I'll be needing more than 7 bytes, but I'll just leave it as it is. The rest of the code is pretty simple. In every loop, the input array is checked for the ready byte. If the ready byte is set, the rest of the array is processed. Depending on the mode, the optional payload bytes are handled as well, and the ready byte is cleared for the next message. After that, the output array is populated with the 7 output bytes which the master will be expecting. Mode, offset and remaining steps. One thing that probably needs some attention is the configuration of the timer. So here's a crappy crash course on AVR timers. Please keep in mind that this explanation only outlines a very particular use case, so it's neither very accurate nor complete. The 85 has a built-in 8-bit clock ticking along with the controller's system frequency, which is set to 8 MHz. That gives you 8 million ticks per second. Those 8 million ticks can be modified using the so-called prescaler, which kind of acts like a divider. So a prescaler of 64 causes the clock to only tick every 64th CPU cycle. As the timer counts up, the controller compares its value, which is a number between 0 and 255, with a certain register called OCR0A. That value, also a number between 0 and 255, can be set manually. Whenever the two match, an interrupt is triggered and the clock starts over. So if OCR0A is set to 0, the interrupt is triggered immediately and you get the minimum tick duration. If you set the register to 255, you get a tick duration that is 250 times longer. The interrupt routine is simply used to toggle some output pin, which will be used to drive a stepper controller. The big question is, what's a good setting for the prescaler, OCR0A, and stepping mode to achieve a certain speed range? I put together the spreadsheet to help me play around with the numbers, but I have to admit in the end it's been kind of a guessing game. So here's what seems to be working fine for my setup. First off, I'll set the stepper motor controller to half stepping mode, which means it will need 400 pulses for 1 revolution. For the top speed, I'm aiming for 1200 RPM because I doubt my motor would survive any more than that anyway. That yields the stepping frequency. Now I'll need to be twice as fast in terms of pin toggle frequency because I need a low to high transition for 1 step. So that would be this frequency. I can now take this and put it into this formula to get the precise interrupt value, which usually isn't an integer, so I gotta round up or down, let's say 61, and that means I'll have a motor speed of 1209 RPM. The low-end calculation is pretty straightforward. I simply enter the highest clock value before overflow, and that equals 293 RPM. So when the controller receives the speed mode message, I just clamp it to the interval 293 and 1209, convert that to the interrupt value exactly as in this spreadsheet but in reverse, and write that to the OCR0A register. Okay, and that's it in the microcontroller department. Compile, upload, plug and play. Let's move on to the hardware. As far as the stepper motor and controller are concerned, there isn't really much to say. The motor has 200 steps per revolution and is rated for around 1.5 amps. The controller is actually part of a 4-piece CNC set. Each controller normally connects to a CNC controller board that plugs into the PC over a serial cable. Fortunately, the stepper controller is independent enough, so I can use it directly with the 85. On the board, there are a bunch of switches that can be used for some tweaking. The most important settings are the current and the stepping mode, which I set to half stepping. The device is pretty tolerant with regard to its supply voltage. I'm going to feed it 24 volts. Regardless of the motor that is attached, the controller will regulate the voltage automatically so that the output current always matches the selected setting. The input is pretty straightforward: 5 volt, logic, enable, direction and step. Before we move on to the demonstration, here's a quick rundown of the whole setup. The I/O Warrior 40, taking the role of the I2C master, connects to the PC over USB. From there, 2 wires, clock and data, connect to the ATTiny85 USI pins 5 and 7. The 3rd wire is ground. The 3 remaining pins, representing enable, direction and step, connect to the stepper motor controller. Because I don't want to suck out too much current out of the I/O Warrior, the 85 and the motor controller get their own 5 volt power supply. That means 4 more wires, 5 volt to the motor controller, 5 volt and ground to the 85. The reset pin also needs to be pulled high. To make sure all components operate at the same ground level, I soldered this jumper cable to the ground of the 24 volt power supply, so this simply connects to all the other grounds. Okay, so as you can see, I have chosen an angle here so you can see both the hardware and the user interface in the background of the monitor. At this point, the buttons don't do anything because the ATTiny85, or rather the reset pin, is connected to ground, so I need to pull that high. And when I do, the UI should turn on. Another thing that I have to do is plug in the 24-volt power supply, which I like to unplug because it's producing some almost unhearable frequency that messes with my recording. If you listen closely, you can probably hear this buzzing sound. Anyway, so let's see. So this is one way, the other way. Apparently I have clockwise and counterclockwise mixed up, but that's not difficult to fix. Modifying the speed. As you can see in this row, the controller keeps track of the steps it's gone so far. So I can stop it and 0 the variable. And now we can test the manual stepping mode. The target step count is set to 200, so that means it's like it should be 1/2 rotation. So this is one way, this the other way. The variable remaining, if you look closely, keeps displaying 0. That's because it processes the number of steps so quickly that it doesn't have time to fetch a number different than 0. So, but if I set this to, I don't know, like 10,000 or something, and we start the stepping mode, you can see how the number keeps going down slowly, and eventually the other variable is going to display exactly that number. There are two major issues I've encountered while working on this program that I'd like to point out. The first thing is the excessive usage of interrupts. Because I'm using different interrupt sources at the same time, for example, the clock overflow and USI functionality, collisions are likely. This leads to communication errors and motor stalling at high frequencies. I've been reading up on alternatives, and I think the ATTiny85 is capable of producing a PWM signal directly on a pin without any interrupt, so this is something I'll try next. The other thing is that increasing the motor speed smoothly is the key to reach top speed. Attempting to start the motor at 400 RPM or so, as you can see, will usually result in immediate stalling. I managed to reach around 1200 RPM with this motor, despite the interrupt collision problem, but it was very sensitive and I can't reproduce it because I changed something in the code and I don't know what it was. So that's it for today, I guess. Some of the code is available if you're interested. Other than that, have a good day.